Hello, welcome everyone to today's lecture on big data. We are about to embark on a journey through the rapidly evolving landscape of data management, exploring its concept, how it is traditionally being stored, and the innovative methods that are shaping its future. Big data is not just a technical term. It's a phenomenon that transforming industries, driving innovation, and challenging us to rethink how we handle information. Let's begin with an overview of what we are going to cover today. We will start by introducing big data and its significance, followed by a broad look at its characteristics and growth. Then we will dive into the traditional methods that have been used to store massive data sets over the years. Finally, we will explore the cutting-edge approach that are revolutionizing how we manage big data by addressing the challenges of scale, speed, and complexity. Data is at the heart of everything we will discuss today. Data is the raw material that fuels insights, decisions, and innovations across every sector. Whether it's a structured data like sales records or unstructured data like social media posts, the sheer volume and variety of data we generate today are unprecedented, setting the stage for the big data revolution. Different items are metaphorically referred to as gold due to their high value or significance. Yellow gold. This refers to the traditional and highly valued from gold used in jewelry as a monetary standard. It's known for its rich yellow color. Then we have green gold. This term is often used to describe forests and trees, emphasizing their immense value in terms of biodiversity, ecosystem services, and environmental stability. Then we have red gold, saffron. Saffron is sometimes referred as the red gold because of its high value and labor intensive harvesting process. So it is considered as the most expensive food in the world. Then we have black gold. This is a nickname for crude oil or petroleum, highlighting its economic importance as a major energy resource. Finally, we have intangible gold, data. This is a metaphorical term used to describe data and information, highlighting their immense value in the modern digital age. Data is considered as a valuable asset for various industries and technologies. The growth of data is indeed staggering. Let's examine the incredible growth of data from 2010 to 2026. According to the data source from explodingtopics.com, we have seen an exponential rise over these years, starting at just 2 zettabytes in 2010. The volume growth steadily to 5 zettabytes by 2011, 6.5 by 2012, and 9 by 2013. By 2014, it reached to 12.5 zettabyte, then 15.5 in 2015, and 18 in 2016. The growth accelerated in 2017 to 26 zettabyte, followed by 33 in 2018, and so on to 181 in 2025, and it has been predicted that it will reach to 215 zettabytes in 2026. This exponential increase is driven by factors such as technological advancement, increased digitalization, and the proliferation of the internet-connected devices like the Internet of Things. This trajectory underscores the urgent need for advanced storage and management solutions to keep pace with this explosive growth. Next, let's consider the proportion of the internet data traffic, which gives us insight into how data is being used globally. First, we have video streaming. Video streaming dominates, accounting for a significant portion of traffic due to platforms like Netflix and YouTube. Then we have social networking. Social networking follows, driven by platforms such as Facebook and Instagram, while gaming traffic is surging with the rise of mobile and cloud gaming. Other categories like web browsing, messaging, marketplace, file sharing, cloud services, VPN usage, and audio streaming also contribute to the mix, reflecting the diverse ways we interact with data online. To grasp the scale of the internet activity, let's look at what happened in just 1 minute online. In that short span, like 1 minute, 5.9 9 million Google search do we have? 1 billion question answered by Siri and other ChatGPT or other friends. We have 3 billion YouTube views, 18 million text messages, and 138 million reels played on Facebook and Instagram, 251 million emails sent, and so on. This snapshot illustrates the dynamic, fast-paced nature of our digital world and the critical role big data plays in management this sheer amount of data. Yes, big data is considered as a buzzword. Big data has become a buzzword for a reason. It's at the forefront of technological innovation. Big data refers to the vast volume of data that is too large and complex for traditional data processing methods to handle. The terminology of big data captures the excitement and potential of harnessing massive data sets to uncover insights, predict trends, and solve complex problems. The terminology has been widely used in news, magazine discussions, conferences, and publications related to data analytics and technology trends. Its popularity is evident across industries, from healthcare to business, where it's driving smarter decisions and new opportunities. Speaking of popularity of big data, let's look at how big data is trending in academic and research communities. According to the Google Scholar, top publications in data mining and analysis under the engineering and computer science categories highlight the prominence of big data. So among the top journals here, we have Journal of Big Data with 79 H5 index and 191 H5 median. And also we have IEEE International on Big Data. So there are very famous journal and conferences. These rankings reflect the growing academic interest and the critical role big data plays in advancing research and technology. The significant growth in the number of Google search for big data after 2010 can be attributed to several factors. So you can see here this Google trends, and the unit is relative popularity or interest. The popularity of the keyword relative to the highest point on the chart for the selected time period and location. So this is the worldwide from 2004 up to 2025. The trend of big data continues to rise as evidenced by its increasing relevance in both research and practical applications. The growth we have seen in data volume combined with advancement in analytics has made big data a cornerstone of modern innovation. Its trajectory suggests that it will remain a key focus for years to come, pushing the boundaries of what's possible with data-driven insights. It seems to be nice job based on the popularity, mean jobs availability is high. What do we need to know to grab some popular jobs? This is a graph to show what are the most popular data science software that are needed for data science job. These data were collected from Indeed.com. So here is job requirements in big data fields. So the first one is SQL, then Python, Java, Hadoop, and the others that you can see here. Professionals in this space need a mix of technical skills such as expertise in data processing frameworks like Hadoop and Spark, as well as proficiency in machine learning and analytics. Beyond technical know-how, they must also excel in problem solving, communication, and understanding business needs to translate data into actionable strategies. To understand big data's role, let's consider the progression from raw data to impactful outcomes. It starts with data, raw facts and figures. Whatever you can save on a computer doesn't matter. It's text, numbers, video, audio, image, etc. These become information when it's organized and contextualized, or you can say structured. Information returned into knowledge when analyzed and understood. Then knowledge can become insights for longer term, and from the insight we can move to wisdom. And from wisdom, we can go to impact when applied to make decisions, innovate, or solve problems. This flow underscores the transformative power of big data. Big data intersects with data science, which is an interdisciplinary field focused on processing large data sets using statistical methods to extract insight. A key component of this is machine learning. This machine learning is a subset of AI, and it's a set of techniques that allows computers to learn from data without being explicitly programmed. Together, data science and machine learning enable us to uncover patterns and make predictions from massive data sets. Big data comes from various sources. Human source data includes social media posts and emails. Then we have machine generated data. They come from the Internet of Things, like sensors in smart devices, smart cities, smart factories, etc. Then we have process-mediated data arises from traditional business systems such as banking transactions. Lastly, derived data is created by processing existing data, like calculating total revenue from sale records. These sources highlight the diversity of big data. Diving deeper into human source data, this category includes content from social networks like Facebook and X, as well as blogs, comments, and personal documents. It is also encompasses photos on platforms like Instagram, the internet searches, text messages, user-generated maps, and emails. This type of data is rich in variety and reflects human interaction in the digital space. Now, let's explore process-mediated data. This comes from traditional business systems, including data produced by public agencies, medical records, and business transactions. Examples include commercial transactions and banking data, which are structured and often critical for operational process. This type of data has been a cornerstone of business analytics for decades. Then we have machine generated data. Machine generated data is another major category, largely driven by the Internet of Things. These includes data from sensors, both fixed like weather or traffic sensors, or mobile sensors such as those tracking phone location or car movements. It is also includes scientific sensors, surveillance footage, satellite images, and logs from computer systems like weblogs. This data is often high volume and generated in real time. Lastly, we have derived data. Derived data is created by manipulating or combining existing raw data. For example, from sales transaction, we can derive metrics like total revenue, average purchase volume, or customer demographics. This type of data adds value by providing new insights through processing and analysis, making it a powerful tool for decision making. So there are 5 V's of big data. The 5 V's of big data are 5 main characteristics that define the nature of large and complex data sets. These V's help in understanding and managing the challenges posed by big data. The first one is volume. Volume refers to the sheer size of the data. Big data involves vast amounts of information that exceeds the processing capacity of traditional database systems. It can range from terabytes to petabytes and beyond, encompassing massive data sets. The second one is velocity. Velocity indicates the speed at which data is generated, collected, and processed. With the rise of IoT devices, social media, and other real-time data sources, big data often streams in at high speeds, requiring rapid processing and analysis. The next one is variety. Variety encompasses different types and formats of data. Big data is not only structured data like traditional databases, but also includes unstructured and semi-structured data such as text, image, video, and social media interactions. The next one is veracity. Veracity refers to the reliability and accuracy of data. Big data can be noisy and may contain errors or inconsistencies. Ensuring the trustworthiness of the data is crucial for making informed decisions. The last one, but not the least one, is value. Value emphasizes the importance of extracting meaningful insight and value from the data. It's not just about the sheer quantity of data, but about driving actionable insights that can lead to informed business decisions and innovations. Understanding these 5 V's help organizations effectively manage, analyze, and utilize big data to gain valuable insights and drive business strategies. Speaking of volume, let's look at the scale of data we are dealing with. A kilobyte, 10 in power of 3, or 1000 bytes. A megabyte is 10 power of 6. A gigabyte, 10 in power of 9. Terabyte, then petabyte, exabyte, zettabyte, yottabyte. These massive units reflect the enormous quantities of data we are generating. As we saw earlier, with global data reaching 215 zettabyte by 2026. Data can be classified by its structure, and this reflects how we store and analyze data. Big data is classified into three main types based on the format and structure of data. The first one is structured data, second one unstructured data, and third one semi-structured data. The structured data is highly organized and follows a specific format. Structured data is easily searchable, as it is typically stored in databases with well-defined schemas. Examples include data stored in relational databases, spreadsheets, or CSV files. Structured data is easy to process and analyze using traditional data management tools. Then we have semi-structured data. This type of data falls between structured and unstructured data. So let's see what is unstructured data. Unstructured data lacks a specific format or structure. It includes a wide range of information like text, image, audio files, and video files. Analyzing unstructured data can be more challenging compared to structured data because it requires specialized tools and techniques, such as natural language processing for text data or image recognition for images. So, semi-structured data has some level of organization but does not conform to a rigid structure like structured data. Semi-structured data is often represented in forms like JSON and XML. It is commonly used in applications where flexibility in data representation is necessary. These classifications are crucial for organizations to determine how to best store, process, and analyze their data based on its format and characteristics. After providing such a long explanation and introduction, we may get some intuition about big data. Now we can define big data. So what exactly is big data? Big data is a collection of data sets so large and complex that traditional database management tools struggle to process them. The challenges include capturing, curating, storing, searching, sharing, transferring, analyzing, and visualizing. These hurdles drive the need for innovative solutions to unlock big data's full potential. The ultimate goal of working with data is generalization. It means creating a model or summarization that captures key patterns and insights. Whether it's predicting customer behavior or identifying trends, this process transforms raw data in actionable knowledge that can drive impact across industries. So what is the objective of working with big data? What to do with this huge amount of data? Intangible gold that is too expensive. Collection data, storing data, processing data are very difficult and expensive. So why we need to pay such cost just to extract knowledge and insight? Because human being is greedy to know. And this knowing helps us a lot to survive based on the Charles Darwin theory. We would like to make a generalization model from the data. Means we want to learn from data and make a model accordingly. Then we can use such models for prediction as an example. This model or summarization of data helps us a lot. It helps us to minimize the cost and remove the need of collecting data again and again. And also, we can use them to do inferential statistics like election, precipitation, prediction. Several contributors enable this generalization. Frameworks like Hadoop file system, Spark, and MapReduce provide the infrastructure for processing large datasets. Analytics and algorithms such as deep learning frameworks, similarity search, hypothesis testing, transformers, recommendation systems, and link analysis help extract insights. Together, these tools form the backbone of big data analytics. Big data has a wide-ranging applications. Healthcare. Big data enables personalized medicine and predictive diagnostics by analyzing vast clinical and genomic datasets. In the case of smart cities, big data supports real-time urban management through data-driven monitoring of infrastructure, energy, and citizen services. In the case of security, big data analytics enhances threat detection and cyber defense by processing large volume of network and behavioral data. In the case of business, companies leverage big data for customer insights, optimizing operations, and driving strategic decision making. We can use big data for predictions. Advanced big data models power accurate forecasting in finance, weather, and demand planning through pattern recognition. And the last but not least, transportation gained a lot from big data. Big data can optimize traffic flow, fleet management, and autonomous vehicle navigation by interacting sensor and GPS data. and many more other applications for big data we can envision. To recap our outline, we have covered the introduction to big data and its overview, including its source, characteristics, and applications. Now, we will move into traditional methods of storing big data, followed by new methods that are addressing the limitations of older approaches. Let's start with traditional methods for storing big data. These include file system, network database models, object database models, XML database models, data warehouses, hierarchical database models, relational database models, object-oriented database models, and distributed databases. Each has played a role in managing data, but often struggle with the scale and complexity of big data. Big data, due to its size and complexity, requires specialized storage methods. Traditional methods are often insufficient for handling big data effectively. So we had file system. File system are one of the earliest methods organizing information in hierarchy. A file acts as a container for data, while directories hold files and subdirectories. Operations like creating, reading, updating, deleting, finding, and navigating are standard. Examples include operating systems like Windows or Unix, as well as network file systems like NFS and NAS, which have been foundational for data storage. Then we have hierarchical database model. The hierarchical database model organizes records into a tree-like structure where records are connected through links. Each record contains fields with single data values, and links form a parent-child relationship. One parent can have many children, but each child has only one parent. Examples include IBM's Information Management System and Microsoft Windows Registry, which use this model to manage structured data efficiently. Then we have network database model. The network database model extends the hierarchical approach by allowing more complex relationships. Unlike hierarchical databases, the network model permits cycle and supports one-to-one, one-to-many, and many-to-many links between records. This flexibility makes it suitable for more complex data structure. An example is the computer-associated integrated database management system, which leverages this model for robust data management. The relational database model is perhaps the most familiar, organizing data into tables with rows and records. Each table has key and non-key fields, and relationships between tables are managed through additional tables. Examples include MySQL, Oracle, Microsoft SQL Server, and PostgreSQL, which have been widely used for structured data but can struggle with the unstructured nature of big data. The object-oriented database model applies object-oriented programming concept to data storage. Object-oriented database model uses classes with properties and behaviors, supports encapsulation and inheritance, and treats data as objects. Examples include DB4O, ObjectDB, and others, which are designed to handle complex data structure more naturally than relational models. The XML database model focuses on storing data in XML format with two approaches. XML-based databases, these map XML data to relational structures, and native XML database which store data directly in XML. Such model is useful for semi-structured data, offering flexibility for applications like content management. Content management systems provide a framework for organizing both structured and unstructured documents. They offer administrative tools, user access control, version control, and workflow to manage data effectively. Examples include WordPress, SharePoint, and other friends which support API like JSR 170 and CMIS for interoperability across diverse systems. Enterprise data warehouses are giant repositories that aggregate data from various sources for reporting, business intelligence, data mining, and analytics. Data is ingested through extract, transform, and load process, and specialized data marts can be created for a specific purpose. These warehouses enable organizations to derive insight from large centralized datasets. And the last one in this category is distributed databases. Distributed databases spread data and sometimes processing across multiple locations. They can be configured for duplication with active-passive setups or replication with active-active setups that require conflict detection and resolution. Fragmentation, such as vertical or horizontal slicing, optimizes data distribution, while semi-joins reduce network costs by combining results locally. To summarize where we have explored the introduction to big data, its overview, and the traditional storage methods that have been used for decades. Now, we will shift focus to the new methods that are addressing the limitation of this elder approach, offering scalability and flexibility for modern data challenges. So let's dive into the new methods for storing big data. These innovative approaches are designed to handle the massive scale, speed, and variety of data we generate today. And the goal is to overcome the constraint of traditional systems and enabling more efficient data management. We had already SQL, now we have two new terminologies, NoSQL, NewSQL. NoSQL and NewSQL represent two pivotal database paradigms that address the evolving demands of big data storage and management. NoSQL databases prioritize scalability, flexibility, and distributed architecture, supporting diverse data models such as key value, document, column family, and graph, making them ideal for handling large volume of semi-structured or unstructured data, typically in modern applications. In contrast, new SQL systems aim to combine the horizontal scalability of NoSQL with strong ACID transactional guarantees and relational model of traditional SQL databases. So we already learned about ACID. ACID is an acronym that defines the key properties of databases that we have already learned: atomicity, consistency, isolation, and durability. NoSQL stands for not only SQL. NoSQL is defined as an approach to database management that encompasses a wide variety of data models, including key value stores, document-oriented databases, columnar databases, and graph databases. NoSQL diverges from traditional relational databases like SQL by offering more flexible and scalable solutions for handling large volume of data with complex structures. NoSQL databases are designed to handle unstructured, semi-structured, and structured data. One of the key advancements is the rise of NoSQL approaches, which are tailored for big data challenges. Unlike relational models, NoSQL databases do not rely on SQL as the primary query language, as may not require fixed table schemas, and often do not support joins. The SQL also may not guarantee ACID properties like atomicity, consistency, isolation, and durability, and typically they leverage distributed computing resources for processing and storage, and in this way they are highly scalable. So we have several categories for NoSQL databases, like key value store like Redis, document store like MongoDB, column family stores like Cassandra, and graph databases like Neo4j. And in case of sharing, we may have horizontal partitioning or breaking a large database into several smaller databases that share nothing together. These types provide flexibility and handling unstructured and semi-structured data, and in this way, they are very ideal for big data applications. Another advancement is NewSQL, which combines the scalability of NoSQL with the ACID, atomicity, consistency, isolation, and durability in the context of SQL transactions. NewSQL systems support SQL, and they are designed for online transaction processing with significant read and write activity. NewSQL use parallel database and multi-processor architecture, such as shared memory, shared disk, or shared nothing configuration. In this way, they can achieve high performance and scalability. NoSQL and NewSQL approach complement the new big data storage methods by providing scalable, flexible, and transactionally consistent database models that leverage distributed, cloud-native, and hybrid storage architecture to effectively manage diverse and large-scale datasets. Here are some of the new emerging methods for storing big data. The first one is cloud native object storage. Examples like Amazon S3, Google Cloud Storage, Azure Blob Storage. They are scalable, cost effective, they support unstructured data with high durability and availability. The second one is distributed file system with erasure coding. Examples are Hadoop HDFS with erasure coding. They have improved storage efficiency and fault tolerance compared to replication. The next one is software-defined storage. They decouple storage hardware from software, and in this way, they can allow us for flexible, scalable, and cost-effective database management. The next one is data lakes with schema on read. They enable storage of raw data in native formats, and in this way, they support flexible analysis and diverse data types. The next one is NVMe over Fabrics. They have high performance storage protocol that extends NVMe SSD benefits over network, and in this way, they can reduce latency. The next one is persistent memory storage. They use byte addressable, non-volatile memory technologies like Intel Optane for faster data access. The next one is blockchain-based storage. They decentralize tamper-evident storage for secure and transparent data provenance. Then we have edge storage solutions. They store and process data closer to the source in order to reduce latency and bandwidth usage, often combined with Internet of Things. Next, we have hybrid storage architecture. They combine SSD, HDD, and cloud tiers dynamically based on data access patterns for cost and performance optimization. And the last but not least one, we have AI optimized storage systems. These kind of storage are designed specifically for large-scale AI workloads. In this way, they can provide efficient data throughput and real-time access. Such methods that I have listed here emphasize scalability, efficiency, and integration with AI and IoT, aligning with the current research and practical needs for big data management. Okay, that's all for today. To wrap up, big data continues to evolve, driven by the need to manage ever growing data sets. The traditional methods we discussed lay the groundwork. But these new approaches like NoSQL, NewSQL, and advanced storage technologies are paving the way for the future, and they enable us to harness the full potential of big data in a scalable, efficient, and secure manner. Thank you very much for your attention. Please feel free to leave your question as a comment below this video lecture. Thank you and see you in the next lecture.